Okay, so in this video I'm going to talk a little bit about magnetic fields, and we're going to look at what a magnetic field looks like, how magnetic fields can affect charged particles, and then later on go on to look at how we can use magnetic fields to build things like motors and applications like cyclotrons and mass spectrometers. Okay, so let's start with some basics. So every student, when they're in year 7 or 8, looks at very basic magnetic fields, and essentially what you do is you plot what a magnetic field looks like. So you should be familiar that a magnetic field around it has these field lines which are often known as fluxons. What you may in addition have realised is that these lines go from north to south. So if you map these using a compass, you see that these lines are directed from north to south. So that's generally speaking what the field around a bar magnet looks like. Okay, so to introduce something a little bit new is the idea of something called flux density, and that's a measure of how many flux lines there are in 1 meter squared at various points. So you can see close to the pole we have a lot of flux lines in a very small space, so that has very high flux density, or what that means is there's a very high magnetic field strength there. So the magnetic field is really strong near the pole. Over here we can see that there are very few fluxons per meter squared, so the field strength at that point is going to be smaller, and generally speaking the further away from a magnet you get, the smaller the flux density, and therefore the smaller the field strength gets. So that was a very simple diagram. We can actually map the whole field for it by chucking a load of iron filings on top of a magnet, and because iron filings are ferromagnetic, which means like iron is a naturally magnetic material, they align themselves with the field, and we can see where all of these field lines are. So this is typically what a field around a bar magnet really looks like when we actually directly map it. And we can see here there's way more flux lines here, so you can see there's a higher flux density around the magnet, and the further away you get, the smaller it gets. So we can see what I was talking about in action with that, and it's because iron is naturally a magnetic material, so it will align itself with magnetic fields. Okay, so that's a basic field. What if we bring two fields together? So we've got two bar magnets. What we can do is figure out what happens when we put them in each other's field. So that's what we can see here, and we can see that their fields are overlapping in this middle section, and they're arranged north to north and south to south. So you should know already with magnets, north poles repel north poles and south poles repel south poles. So you should expect that these two are going to repel each other, and in fact that they do. But we can explain that in terms of flux density. So here in the middle, what we've got is a region of very high flux densities because the two field strengths add together because they're in the same direction at that point. Outside we've got regions of lower flux density because they haven't overlapped at this point, so they haven't really added together. So one of the most fundamental laws of everything in the universe is if you have a difference in something, that creates something to get rid of the difference. So if you have something that's really hot and something that is really cold, energy goes from the hot one to the cold one, and it's the same here. The system is going to act to get rid of that difference, and it does that by inducing this magnetic force which forces them apart so they're no longer in each other's fields, and it eliminates that difference. So that's why you get repulsion when you put two magnets parallel like this. Let's try it again, but with them flipped around. So you should expect that these would attract because a north and a south attract, and a south and a north will attract, and in fact they do. So here we can see their fields are in opposite directions when they overlap here, which means they're going to cancel each other out. So you get a region of very low flux density in the middle and a region of higher flux density outside. So what that's going to do is act to push them closer together, to go from high to low, so when they come in contact with each other, that evens out the magnetic field and you get rid of that difference there. So that's generally speaking what's going on with two magnets. Now let's explore what happens to charged particles when we introduce them to a magnetic field. Okay, so you can do all sorts of experiments to investigate the effects, and when you do that, what you find is that the force a charged particle experiences from a magnetic field is dependent on essentially three things. It's dependent on the flux density of the magnetic field, so the higher the flux density or higher the field strength, the bigger the force. That's not too surprising. It also depends on the magnitude of the charge. So the bigger the charge is, the bigger the force from the magnetic field. Again, not too surprising. And then there's this last one that is more interesting, is you notice the force actually depends on the velocity of the particle. And it's not just generally the velocity, it's the velocity perpendicular to the field. So essentially the velocity in this direction. So if I call the angle between the velocity and the field theta, the velocity perpendicular to the field is given by v sine theta there. So let's look at what we can do with these principles. So one of the interesting things you notice about the force from a magnetic field is not only we can work out what its magnitude is, but it always acts perpendicularly to the velocity of the charged particle, which is really useful because we can use it to create scenarios with circular motion, because for circular motion we need the resultant force to be directed towards the centre of the circle perpendicular to the velocity. So one application of this is a cyclotron. So what you have here is you put an ion or a charged particle in the centre of your cyclotron, and you use an electric field to increase its velocity. And then from the magnetic equation that we had earlier, we know if we increase the velocity of a charged particle perpendicular to a field, we can increase the magnetic force from that acting on that particle. So then if we equate that force to the equation of centripetal force, which is what we've got here, what we can do is get an expression of the radius of the circle in terms of these things, all of which are constant apart from velocity. So if we can use our electric field to accelerate or increase the speed of our particle, we can increase the radius of the circle, which is why we get this quite nice spiral coming. And when we reach a certain radius, we know we've reached a certain velocity that we might want, we can take that ion out of it by turning off our magnetic field, and we've got a very fast moving charged particle which we can use in a particle accelerator like the LHC at CERN, for example. Okay, so that's one application. Another one being mass spectrometry. So a mass spectrometer uses the fact that different mass will travel in different directions instead of different velocities. So what you do is you've got a sample and you want to know what's in that sample and how much of each element there is in your sample. So what you do is you put it in this part at the end and you heat it up because you want to allow some electrons to escape to leave behind ions. Once you've got ions, you can accelerate them in an electric field, and you use something called a velocity selector to make sure all of your ions are travelling at the same speed. That's what you want. So then, if they're all travelling at the same speed in the same magnetic field, and we ionize them all to the same charge, and our velocity selector will essentially make sure they're all the same charge and the same velocity, we can see that different masses will take different paths through and to our detector, and by looking which mass goes which way and how many of the masses go that way, we can work out what's in our sample and what percentage of our sample is each element there by applying the stuff we know about magnetic fields. Okay, so there's a few applications. We're going to finish looking at charges in a magnetic field by talking about the direction of the force. So I told you a moment ago the force always acts perpendicular to the velocity as long as the velocity is perpendicular to the field. So there's a lot of things that are perpendicular to each other. Let's see what that looks like. So many of you may have come across this before at GCSE. It's called Fleming's left-hand rule, and it allows you to work out the direction of the force based on the field and the direction of the charged particle. So, with it set up like this, your thumb represents the direction of the force, your first finger represents the direction of the field, so it should point from north to south, and your middle finger represents the direction of the velocity perpendicular to the field, so the v sine theta effectively. So, this will tell us the direction of the force on a positive particle. If we want to know the direction of the negative particle, it's just going to be in the opposite direction. So if your thumb's pointing up, for a negative particle, that means that's down. So let's go back to what we were looking at earlier. So we had this example. So our field is coming from left to right, because that's the direction of the field lines. Our charged particle, positive, v sine theta, is up. And therefore, what we can see is the force is going to be going into the plane of the board, and it's going to be going normally or at 90 degrees to the board there. So our positive particle would go into the board here, and our negative particle therefore would come out of the board there if it was negative, not positive. So now what we know is we can work out what the magnitude of the force is, and we can work out the direction of the force, so we can predict what will happen to charged particles when we put them inside a magnetic field. Okay, so that finishes looking at individual charges. What we're going to do now is move on to look at lots of charges all moving in the form of currents in wires, and how that can apply to creating a motor. Okay, so what we've got here is a wire carrying a current, and we know to have got a current we must have applied a potential difference across our wire. So that's what we've got. So we know current is the rate of flow of charge around a circuit. So essentially we know if there's a current, we know that charges are moving through this conductor. And if we've got moving charges, we know they can experience a force from a magnetic field. So if you can experience a force from a magnetic field, that must mean you yourself have a magnetic field, because it's the interaction of two fields that creates forces on things. Okay, so what we're going to look at now is how we can actually map what the field looks like around a conductor or around an individual charge. So when they did all these experiments, they thought that electricity or current was the flow of positive charges, and this goes right back to the work Ben Franklin did on early stage of electricity. So they thought current was the flow of positive charge. So everything they've done is defined in terms of that, and that's called conventional current, the flow of positive charge. So all of these laws depend on the direction of conventional current, not the electron flow. So let's say conventional current is going that way, which means the electrons actually were going that way. And what they discovered is if your current is flowing that way, the field would go around it, going clockwise around the wire. So from this way, you can see it's going around clockwise. So if you get the conductor and wrap your hand around it and put your thumb in the direction of the current, you'll see that the field is going clockwise around that wire, which is and it's called the right-hand corkscrew rule often. Okay, so that's how we can tell the direction of a field around a current-carrying conductor. So each individual charge will have a circular magnetic field around it, and if we have a lot of charges moving, that means we've got a field all the way along this wire as long as it's carrying a current, so the charges are moving. Okay, so that's the corkscrew rule. So what we're going to do is go back to what we were looking at before. So we've done it by experiment what the force on an individual charged particle, so they went back and did the same with a current carrying conductor, and you end up with very similar kind of equation. So the force on a current carrying conductor depends on the field strength. Seems to make sense. It depends on the current. So the bigger the current, the bigger the force, which makes sense because a larger current means the electrons are moving faster. And again, depends on the angle to the field. So essentially, if you have a longer wire in a field, there are going to be more charged particles in it, so a bigger force, makes sense. But if the wire is parallel to the field, that would mean the velocity of the particles is parallel to the field, so it experiences no force. So that's why we've got this sine theta in there. We want to know the direction of the length, and we want to know the component of the length perpendicular to the field, because we want to know the velocity of the particles perpendicular to the field there. So that kind of relates to what we've seen before. So what we can do is relate this back to the original equation we had. So we used to had an equation called F equals BQV sine theta, and now we've got BIL sine theta. So what we can do is relate the two. So we should know that current, or I, is the number of charges per second. So it has a unit of coulombs per second. So if we multiply current by the length, because we have BIL, so current times length, has the unit of coulombs meters per second, which is charge times velocity. So you can see that IL and QV dimensionally are exactly the same, which is nice. So essentially these two are expressions of exactly the same equation, just with different properties used. Okay, so this is actually one of the required practicals in the A-level course, doing this experiment that derived that equation. So what you'll do is you'll use a balance as a way of measuring the force on these, essentially this magnet. Because if this magnet is exerting a force on the wire, Newton's third law tells you the wire will exert an equal and opposite force on the magnet setup. So if an upwards force is induced on the wire, this will be pushed down into the balance, increasing the balance reading. So before you even start, what you do is zero your balance, so it's not taking into account the weight of your magnets, and then as you change the various parameters like the current or the length or the field strength, you can see what the force from the magnetic field is by the reading on your balance. So that's what you do, and in the experiment what you'll be able to do is change the current using an external resistance to allow you to do that. You can change the length of the conductor in the field, you can change the field strength by adding more magnets, or you can change the angle of the wire to the field to see the impact of that. So you'll investigate those different things, and what you'll come up with is the equation we've talked about, BIL sine theta, to model it. Okay, so what I said earlier is we're going to look at how all that relates to how an electric motor works, and this is typically how most motors function. So let's have a look at that now. Okay, so just to generalize what we're looking at here, so I'm modeling a motor as, for now, just one coil, and I've called the size of the coil different letters. So this one's A, B, C and D, and you won't be able to see it because it's quite faint, but we've essentially got a current going round this way in our coil, which we're supplying from some external supply over here. Now we've got our magnetic field lines coming across here from north to south. So we look at side A first of all. So the current in A, and therefore the velocity of the particles, is parallel to the field. So side A will experience no force, and the same for side B, because the electrons or positive particles, because we actually really think of the flow of positive particles for this kind of stuff, are moving parallel to the field. In B and D, however, we can see that the conventional current is going this way and this way, which is perpendicular to the field, so they will experience a force, and a force equal to BIL, because they're at 90 degrees to the field. So that's what we've got to start with, but the current is going around this way, so in B, current's going down, like this way, in D it's going this way, so they'll experience equal but opposite direction forces there. Okay, so that's in terms of forces. Now let's look in terms of moments of torque, because we're dealing with rotation here, so we need to think about moments. So, let's first figure out what direction the force is in. So in B, the current is coming down this way, but the field is going across the page. So the force is going to be up. So we said earlier that D is going to be the same force in the opposite direction, so we know the force on D is down. We've got an axis of rotation, so this is the axis on which we're trying to rotate the motor. So you can see these forces are an equal distance from the axis of rotation. So we've got the same force and the same distance, but acting to rotate in the same direction. We've got what's called a couple here. So two moments equal, trying to rotate it in the same direction there. So that's what's going to happen. So these forces are going to try and make the motor flip around this way here. So let's actually do some calculations to see what the magnitude of that torque or moment will be. So we know the force on B and D is going to be BIL. And if I call length A and C W, because it's like the width of your coil, what we can see is the moment of the force on B is going to be BIL times W over 2, because that's the perpendicular distance from the force to the point of rotation. So we've got two of those, because these two are going to add together, so we end up with the total torque is BIL times the width of our coil there. So this is where we're going to get the maximum torque on our motor. So the torque is going to vary as it rotates around, but this is the position of maximum torque we can get. If we rotate this around, so if we let it rotate 90 degrees, we can see that B is now going to come up to the top, D is going to go down, and then we're going to be looking essentially at side C over here. So that's what we've got in this diagram. We've rotated it around, so B's at the top, D's at the bottom, and we're looking at side C. So the first thing to notice now is all of the currents are now perpendicular to the field. So all sides here will experience a force. So that's what we've got here. So the force on either B or D is BIL, and the force on either A or C is BIW, because that's the length of those sides. So, in terms of the direction of them, well, we know that the field is coming across this way, so the current is going round this way, so it's coming out of B and then down here. So for B, we can see if we put the field across and the current coming out, the force is going to be upwards. D is therefore going to be downwards, and if we do it for C, the current is coming downwards, field's going across, so for C, the force is coming out here, so for A, the force is going into the board there. So those are the directions of all of the forces. Let's look at torques, however. So if we look at these, the line of action we can clearly see, so your axis of rotation is like into the board here, so this line of action goes straight through that, same with this one, same with C and same for A. So actually, none of these forces will have a moment about the axis of rotation. So at this point, the torque on the motor is 0. So by rotating 90 degrees, we've gone from maximum torque to 0 torque at this point here. And this would be a problem if we were trying to start this motor. Now, we couldn't. So actually, most like electric motors have some magnets here, like sort of around here and here, to essentially make the coil not be perpendicular to the field like this. So that's something they can take care of in designing a motor. So let's take it back a little bit. So we've gone around 90 degrees. Let's take it back a bit, maybe like 6 degrees or something around like that. So let's rotate it back slightly here. So what we can do is think about first the lines of actions of the force that would act on C or on A. So they will always be sort of like in this direction or this direction, or they may turn out to be 0, but they're always going to be going through the axis of rotation. So those forces are never going to have a moment, so we don't need to consider those. But the forces here and here will have a changing moment. So what we need to do is figure out what the perpendicular distance is from the line of action of this force to the axis of rotation, which is this distance here. And we can see that that's going to be, if this is W, this is W over 2, and we're going to want W over 2 cosine theta is the perpendicular distance. So the moment of D, or the moment of B, is going to be given by this expression. We've got 2 of them, so the total torque can be expressed by this function, BILW cosine theta, where theta is the angle between the plane of the coil. So imagine the coil is like this. Now that's the plane of the coil, and this is the direction of the field there. So we can actually map it as a function. So when we put theta equals 0, we get a maximum, and when we put theta is 90, we get 0. So that maps what we've talked about already there. Okay, so in the scenario where it's now rotated 180 degrees, B started here, so B is now over here. So originally, B experienced an upward force to make it rotate up this way. So we know the current is coming up through B, around C, and into it at D. So if we put the current going into the board at D, rotate so we've got it in the direction of the field, we see that D now experiences a force this way, and essentially B will experience a force this way. So it's trying to rotate back to where it was before. So that's actually what happens with a motor if you don't do anything about it. It will just flip-flop between the 2 positions, never actually doing a rotation if you don't change anything about the circuit. So to make it do a complete rotation, what you have to do is change the current direction. So if here we flip the direction of current, this will now experience a force to make it continue rotating in the same direction, which is what we want. And when you flip the current, is you flip the current when it's at these positions here. So when it's rotated 90 and when it's rotated 270. Those are the positions you flip the current to make sure the force is always going in the direction of rotation. And the device you use to do that is called a commutator, which is a really fancy word for just 2 wires or brushes. So when the motor is flipped around, these brushes make contact with the opposite connections and it flips the direction of the current, which allows it to keep rotating in the same direction. So that's what your commutator was there for, to keep the force or the torques acting to rotate in the same direction there. Okay, so that finishes this video looking at magnetic fields and their impact on charges and on current carrying conductors. In my next video, I'm going to look at how we can use these principles to actually generate electricity in the form of electromagnetic induction. So I hope you found this useful. If you have any questions or things that are not clear, please do comment and let me know. I'll be happy to clear those up for you. But as always, thank you for taking the time to watch this video.